Welcome back to the CCNA routing and switching video series brought to you by ABY Design and Tech. In this video we will have a deep dive look at TCP and have a look at all the features of what makes TCP one of the most popular layer 4 protocols today. So TCP is a layer 4 protocol. It operates at the transport layer of the OSI model. That's TCP and UDP, the most popular layer 4 protocols used in modern networks. Now, TCP and UDP, they define how we send data. Either we send it reliably or we send it in an unreliable fashion. And they also define to what software application the data is destined for once the data reaches the destination device. Now, TCP is best used for data applications like website browsing, etc., file transfer, purely because of the features that TCP offers. TCP ensure delivery of data. TCP ensures that if data is stopped, it can retransmit that data, etc. UDP, user datagram protocol, sends data in an unreliable fashion in that it doesn't promise that the data will get there. TCP promises that the data will get there, and it will actually check with the receiving host that it's received the data that it's just sent. UDP does not. Now, the reason why we use UDP is because it has a smaller header, which means that a UDP packet is going to be of a smaller size, which means it can get from point A to point B quicker than a TCP packet. But most importantly is that for real-time applications like voice calls and video calls, UDP is perfect. Because voice and video calls, they don't need all the features of TCP. We don't need to retransmit a voice packet which dropped 20 seconds ago. For voice and video calls to be successful or to have a good quality, we have to ensure that the voice or video packets are delivered from point A to point B as quickly as possible to ensure that the voice or video call is smooth. Now, TCP and UDP, they tell the receiving device to what software application the data is destined for by using port numbers. So a port number is a 16-bit number that's used to identify the specific application or services, and we have a source port and a destination port. Source port, what application this data was coming from. Destination port, what application this data is going to. The port numbers range from 0 through 65,535, and it's a combination of IP address and port number, which is known as a socket, that delivers data to the correct application on the correct computer. Think of this like a block of flats. So flats in the same building will all have the same street address. The street address represents the IP address. Okay. However, we can identify each flat individually by the flat number. The flat number is similar to the port number in that the port number identifies the software application that the data is destined for. That specific software application, when there could be multiple software applications running on the computer at the same time. So just like with IP addresses, port numbers are broken up into different sections. So we have 0 through 1023. So the first 1024 port numbers are called well-known port numbers, and they are reserved for server services such as HTTP or HTTPS, FTP, etc. And the reason why they're reserved is because these are going to be services which, as clients, we are going to be accessing on a regular basis. So because they're going to be accessed on a regular basis, they need to have a well-known port number, or a port number which stays the same. So no matter what server we're talking to or what client we're coming from, we can ensure that we're speaking to the correct services running on the server. So as an example, HTTP uses the well-known port number of 80. So no matter which web server we're speaking to, we can communicate with the web service running on the web server by just setting the destination port to port 80. So it allows reachability to the services, no matter what server you're speaking to. Port numbers 1024 through 49,151 are semi-reserved, and they can be registered for services by contacting the IANA. So imagine that I want to set up a service. I can use a port number from that range to essentially reserve that for my particular application or my particular service that I want to run on a server. And the IANA are the Internet Assigned Numbers Authority. Now, port numbers 49,152 through 65,535. These are port numbers which are used by client programs, and they are known as randomly generated port numbers, in that when you open up your web browser, it needs to associate a port number with that application. It's going to generate a port number within this range and assign that to the application. As soon as you close down that web browser, that port number disappears, and then when you open up the web browser again, it's going to generate a new port number from that range. Now, let's have a look at how IP address and port numbers allow for complete communication. Okay, so in this case, the client on the left is communicating with the web server on the right. Okay, now the source field is going to contain the laptop's or the computer's source IP address. Now, the source port number is going to be the application or the web browser application the user opened up and then search for youtube.com in the address bar. So obviously we're going to be contacting youtube.com. Okay, so that means that the user, let's say Bob or Larry, etc., whoever, has opened up a web browser and they've searched in youtube.com into the address bar. That port number is going to be the web browser application that the user performed that action on. Okay, the destination IP address is obviously going to be the IP address of the web server hosting the youtube.com website. Again, the computer gets this by using DNS to say, I have the domain name or the name youtube.com. Can you tell me what the IP address is for the server which is hosting youtube.com and has the name youtube.com? And this is the IP address which was returned from the DNS server. This is not the actual IP address of youtube.com. You can find that by using a NS lookup. So that's the destination IP address, and obviously the destination port number is going to be the well-known HTTP port number of 80. The reason being because the client wants to communicate with the web services running on that server, and it knows that web services, they use the well-known port number of 80. So I'm going to set the destination port number to 80 so I can communicate with the web service application running on that server. And so the server receives that HTTP GET request or the data from the client. Is going to send it over to the web service application to process it. The web service application is then going to respond with the youtube.com homepage. So the YouTube homepage is going to be sent to the client. Again, the packet is going to be sourced from the IP address of the youtube.com server. It's going to be sourced from port 80, which is the web services running on the server. So the port number used to identify the web services running on the server, and the destination is going to be the IP address of the client, and the destination port number is going to be the port number associated with the web browser that the user searched for youtube.com on. Okay, so that web browser that the user opened up and typed in youtube.com, that's going to be the destination port number to ensure the data is delivered to the computer and displayed on the correct web browser and on the correct tab. Now let's have a look at some well-known port numbers which are associated with TCP. FTP, which is a file transfer protocol, is a file transfer application allow you to transfer files over the network to a server, uses port numbers 20 and 21. SSH, which allows for secure remote management of Cisco devices, will use port number 22. Telnet, port number 23, which is used for unsecure management of Cisco devices. So essentially any configuration commands you are typing in on the Cisco device will be sending cloud text, which is not secure. Then we have SMTP, which stands for Simple Mail Transfer Protocol. This is a mail service which will use port number 25. DNS, which will use port number 53. HTTP, which is to hold websites, retrieve websites over the network, we'll use port number 18. POP3 will use port number 110. POP3 and IMAP4 are both mail services. IMAP4 will use port number 143, and HTTPS, which allows for secure communication or secure retrieval of a website, will use port number 443. So now let's have a look at the TCP header. Okay, the TCP header can have a minimum length of 20 bytes and max length of 60 bytes. And the TCP header is going to add it to the data after the data has been built. So basically we build the data that we're going to send, then we put a TCP header onto that data. That TCP header will be defining what application sent this data and what application this data should be going to. So the first two fields of the TCP header, the source port identifies the sending application, essentially what data on the sender sent this data. The destination port is going to identify the application this data should be going to on the receiving host. Then we have the sequence number, which is 32 bits in length. It's a 32-bit number, and it is used to keep track of how much data has been sent. Okay, and so essentially the application is not going to give a whole chunk of data to the TCP protocol. The way that it works is that the application will actually send one byte of data down in a data stream to the TCP protocol. Then the job of the TCP protocol to package these individual bytes of data into a segment. So think of a segment as containing multiple bytes of data, and then sending those multiple bytes of data over to the receiving host. Now, each byte of data in the data stream is assigned a sequence number. Sequence number is what allows TCP to perform retransmission of lost packets, reordering, etc., acknowledgement of packets. It's a sequence number which allows for the reliable communication that TCP provides. And so the sequence number is super important for reliable delivery of data, but it's also used to keep track of where we are in the data stream in terms of what bytes have already been sent. So you have to remember that what the sequence number tells us is whereabouts we are in the overall transmission of this data stream. Okay, so obviously bytes which are earlier in the data stream are going to have a lower sequence number than bytes that are halfway through or at the end of the data stream, which are going to have a higher sequence number. So essentially it will say to the receiving device, or essentially will let the sending device know, but essentially it will tell the receiving device that I'm, let's say, halfway through this overall stream of data that the application wants to send to you, or I'm at the end of the stream of data that the application wants to send from you, just from the sequence number. That this will become more prevalent once we go through some TCP examples of how TCP works. The next field we have is called the acknowledgement field. Okay, the acknowledgement field is a 32-bit number, and it's to acknowledge the receipt of data packets. So it's essentially what the acknowledgement field says is that not only have I received the data that you have just sent me, Mr. Sender, but I've also listing the sequence number that I expect to see in the next TCP packet. So just to show you that I've actually received your data, I received all the data that you've sent so far, and I expect for the next TCP packet to have this sequence number. And this, by using this sort of methodology, it allows the sender to essentially transmit multiple TCP packets to the receiver, and then the receiver to use a single acknowledgement to acknowledge receipt of all those packets. The next field we have is data offset. This is 4 bits, and this defines the size of the TCP header in 32-bit words. And so essentially what it tells the receiving device is that this is how large the TCP header is. That taking this into account, it also lets the receiving device know where the data starts. We have the flags field, which is 9 bits in length because it holds 9 flags. And there's 1 bit for each flag. The flag fields are used for control bits. So it's used to establish and terminate connections and also send data. So we have the SYN flag, which is used to set up a TCP connection between hosts. We have the ACK flag, which indicates that the ACK field has significance, but also if it's set to 0, it means that we are not acknowledging any receipt of any traffic. Then we have the FIN field. Okay, the FIN field, the FIN flag is used to bring down the TCP connection when there's no more data to be exchanged. The next field we have is the window size field. Okay, so the window size is used for flow control. It's essentially telling the sending device or the sending application, this is how much data you can send to the receiving application or receiving device at one time. And so the way that it works is that as the receiver starts to receive more and more traffic, and that traffic is going to be transmitted successfully without any packet drops, it's going to increase the window size. So the window size will increase, and the sender can then start sending more data. If any packets are dropped during transit, it's going to reduce the window size, and okay, buddy, we've chanced our luck. We tried to send X amount of data, and obviously we lost some packets. So let's play it safe. Let's drop the window size in half. Then once we can exchange that amount of data successfully, I will start to increase the window size, and then you can start to send more and more data at one time. And so the way that it works is that it's how much data the sender can send to the receiver at once before the receiver has to acknowledge the receipt of that data. And then what this allows the sender and receiver to do, it allows the client, the sending device, to send a whole bunch of data, and allows the receiving device to acknowledge receipt of the data with just a single acknowledgement packet. Then we have the checksum field. Now the checksum is just used to ensure that the TCP header hasn't been changed during transit, has it become corrupted during transit. The urgent field, which is points to the urgent data byte if the urgent flag is set to 1. And then we have the options field, which is optional, and it's described in 32-bit words and can be anywhere from 0 through 32 bits. Now that we've had to look at the TCP header, let's have a look at some of the features of TCP. So TCP, which stands for Transmission Control Protocol, it provides reliable delivery of traffic. Now TCP does this by establishing a TCP session between the sending and receiving host before any data is sent. So before any data is sent, this TCP connection is established. This TCP session is established. The TCP session will remain active once the sending and receiving hosts exchange data, and once the two hosts have finished exchanging information, have finished communicating, the TCP session will be torn down. And so an easy way to visualize this is that when you open up your web browser and you browse to a website, before the website is even displayed on your screen, your laptop, your computer, and that web server which is holding that website, they're going through the process of TCP session establishment. Essentially, they're establishing that TCP connection, okay? Once that TCP connection is established, data is sent from the server to your computer. So in essence, that website that you were looking at is now displayed on your computer screen. As you are on the website and you go to the different pages of the website and you browse the website, that TCP connection will remain active because you're still on that website. You still have to communicate with the web server to retrieve the web pages that you want to access and to send data to that server of each click, every payment you make, etc., whatever. And then once you've closed down your web browser, that's going to be TCP session termination, because you no longer need to exchange data with that web server because you're no longer browsing that website. Now let's have a look at some TCP message types. Okay, so we have the SYN message, which is used to initiate and establish that TCP connection between the sending and receiving host. This also has both sides synchronize the sequence numbers that they will use to send data. Okay, so obviously both sides have to use sequence numbers for their data, and we'll talk about why in a bit. This essentially allows both sides to say, I'm going to start with this sequence numbering, I'm going to start with that sequence numbering, and so that they both know what the starting sequence numbers are going to be from both sides. The ACK field confirms the ACK message type confirms receipt of the SYN message and the data. The SYN ACK is a SYN message from the local device and the ACK for the earlier packet, and the FIN message type is used to terminate that TCP connection. So now let's have a look at TCP connection establishment, what happens during the connection, and also TCP connection termination. Okay, so connection establishment is performed using the TCP three-way handshake. So the TCP three-way handshake will most of the time be initiated by the client. So in this case, the laptop. And as an example, let's just imagine that the user on the laptop wants to access a web server. So it's going to send a SYN message, okay, to the server saying that I want to establish a TCP connection with you. It's going to then randomly generate a sequence number saying that this is the sequence numbering that I'm going to start with. I'm going to start numbering my sequence numbering from 321. So this is the first packet I sent you. It's going to have a sequence number of 321. The packets I sent after are going to have a higher sequence number after 321. The server responds back with a SYN ACK. So the SYN ACK basically says, okay, let's have a look at the ACK first. The ACK says, I've acknowledged receipt of your SYN packet because I've listed the ACK with a ACK number of 322. The ACK number of 322 essentially says that I've received your SYN packet with a sequence number of 321, and I expect that the next packet you send me should have a sequence number of 322. The ACK in the TCP three-way handshake is always one more than the sequence number of the SYN packet. Now it's going to send a SYN packet to the client saying that I'm going to begin my sequence of numbering starting from number 987. So that's the sequence number of the SYN packet. The client responds back with an ACK acknowledgement, a ACK packet, and the ACK number or the acknowledgement number is going to be 988, saying that okay, I've received your SYN packet. The next packet that I expect to see from you should have a sequence number of 988. That's the TCP three-way handshake complete. And that's now the TCP session established between client and server. Now let's have a look at what happens after the TCP three-way handshake. So obviously after the handshake, after that connection has been established, they're going to start to exchange data. So in this case, the client is going to send a data packet with a sequence number of 322, and that TCP packet is going to have 400 bytes worth of data. The client receives it, and obviously with TCP, sorry, the server receives it. Now with TCP, each host has to acknowledge receipt of the data which has been transferred. So obviously, now that the client has sent a packet to the server has to acknowledge receipt of that packet before it can then transmit its own data. So in this case, it sends back a acknowledgement with a acknowledgement number of 722. Where did they get that acknowledgement number from? Well, the way that it works is that with TCP, obviously each byte of data is assigned a sequence number. So the client on the left told the server, I'm going to begin my sequence numbering starting from sequence number 321. So obviously that was the sequence number included in the SYN message that the client sent to the server. That means that the first byte that it's going to send to the client, to the server, is going to have a sequence number of 322. The next byte's going to have a sequence number of 323. Because you have to remember that the application is sending individual bytes to TCP to send, and TCP is going to be putting a sequence number on each byte. Now, it doesn't transmit each one byte at a time. Essentially, it transmits a whole bunch of those bytes, but by packaging them into a TCP segment. So what it's saying now, so this is what the packet says, is that I'm sending you a whole bunch of data. So I'm sending you 400 bytes in this packet. Now the sequence number of the first byte in this packet is 322. What the server is saying to the client is that the next whole bunch of data you are going to send me, the first byte of that packet should have a sequence number of 722. So I've acknowledged receipt of the packet that you just sent and the 400 bytes of data that you just sent to me. So if you're going to send me another 400 bytes of data, the first byte of that packet should have a sequence number of 722. So I expect that packet to have a sequence number of 722. Now, the server is, now that it's acknowledged receipt of the data that the client has sent, the server is now free to send data to the client. In this case, the data is going to have a sequence number of 988. If you go back to the TCP Connection Establishment, the client told the server that the next packet I expect to receive from you should have a sequence number of 988. Essentially, the server is going to start numbering the bytes is going to send, or the bytes it's receiving from the application. It's going to start with a sequence number of 988 for the first byte, 989 for the second byte, 990 for the third byte, etc. It sends a packet with a sequence number of 988, 700 bytes of data to the client. The client then acknowledges receipt of that packet, because with TCP we have to acknowledge receipt of every packet the sender has sent, or every bit of data the sender has sent. It's going to send back a acknowledgement with a sequence number of 1688. Now, as you can guess, that's 988 plus the 700 bytes of data. So what it's telling the server is, I received that data that you just sent me. I have received the 700 bytes of data that you just sent to me. I expect for the next packet for you to send to me should have a sequence number of 1688, because that should be the sequence number given to the first byte of data in that packet that you are going to send. And it will continue on like that. So in this case, if the client sends over a packet with 1000 bytes of data, that packet is going to have a sequence number of 722, and it's going to carry 1000 bytes of data. What do you expect the acknowledgement number to be from the server once it's received that? And if you probably guessed right, it's going to be 1722. So it's going to say, I've received that data, that packet, that TCP packet, and the 1000 bytes of data which you have just sent to me. I expect for you to send me over the next packet that you send me over is going to have a sequence number of 1722, because that's going to be the sequence number assigned to the first byte of data in that packet. It's literally as simple as that. And so obviously this when the server, so let's go back to here, when the client receives a acknowledgement number of 722, it knows for a fact that the only way it could have worked out that number is if it received my packet with a sequence number of 322 and also all 400 bytes of data within that packet, which means that the next packet I'm going to send, that first byte, is going to have a sequence number of 722. Now, once all data has been exchanged, established, etc., we're going to terminate that connection, and it's just a process of fin ACK, fin ACK. So I want to terminate a connection. I acknowledge that you're going to terminate that connection. And then the server says, I'm going to terminate the connection. And the client says, I acknowledge that you are going to terminate that connection. The connection is terminated. This is, if you want to compare it to something in real life, this is like you going onto youtube.com, browsing through the different pages, watching different videos, and you close it down your web browser. You're shutting down the TCP connection because you no longer need to have a TCP connection with a server established, because you're not, because you are not trying to exchange any data. Now let's have a look at some TCP features. What makes TCP TCP? So TCP provides reliable delivery of data through the process of sequence numbers and acknowledgements. Essentially, every packet sent by either host will have a sequence number, and each packet or block of packets need to be acknowledged by the receiver to ensure that the host that sent those packets has been delivered. So essentially, it ensures to the sending host that those packets you send have actually been delivered to the receiving host. TCP also uses sequence numbers of packets to reorganize the packet into the correct sequence if they're both out of order. So like I said, is that each byte represents, so each byte has a sequence number. Essentially, each byte represents the total amount of data that the sending application wants to send. So if you imagine a stream of data, but let's say packets with a lower sequence number represent earlier in the data stream. Packets with a lower or higher sequence number represent later on in the data stream. So through this sequence numbering, it knows that if it receives 3 packets, and maybe it receives a packet, the third packet it receives has a highest or a lower sequence number than the second packet it received. It knows, okay, the third packet I received, I should have actually received second so for whatever reason, the packet was delayed in reaching me. So now when I actually feed this data to the application, I'm going to feed the first packet I received, then the third packet, then the second packet. And again, we'll see examples of this. TCP also allows for flow control by using a concept called TCP sliding windows. Essentially, we can increase or decrease how much data the sender can send to us before we need to acknowledge receipt of that data. And TCP also uses secret numbers of packets to drop any duplicate packets it receives. So in essence, for some reason, let's say that the receiver receives 2 packets with the same sequence number, it's going to drop one of those packets because the duplicate packet is not going to feed duplicate information to the application. So now let's have a look at some of these features. I find that it's better to view it from a graphical representation because that helps us understand it easier. So let's have a look at TCP windowing. In this example, increasing the window size. So in this case, the client is going to send 400 bytes worth of data to the server. The server is going to acknowledge receipt of that data, and then it's going to increase the window size to 4,000, saying that, okay, now that you've sent me 400 bytes worth of data, you can now send me 4,000 bytes worth of data before I have to acknowledge, because that's how much data the application can now handle. So in this case, the client receives that. He says, okay, the server's received the first packet I sent. He wants me to now send 4,000 more bytes of data. Obviously, I can't send a packet which contains 4,000 bytes of data, so obviously I have to split that down into individual packets. So it sends 2 packets with 1,500 bytes worth of data, 1 packet with 1,000 bytes worth of data. Okay, the server is going to receive those packets successfully, and is going to say, okay, to acknowledge receipt of all that traffic, I'm going to send back an ACK message, but with a acknowledgement number of 4722. This means to the client that, okay, all the data that I sent, the server must have received it, because he's sending back a ACK message with a number of 4722. That means that he's received the first packet I sent with a sequence number of 722, as well as the 4,000 bytes of data that I just sent. That he's received all 4,000 bytes worth of data. Now I'm going to send the next block of data to the server, okay, because I know that he's received 4,722 bytes of data, because each piece of data is given a sequence number. And then the server in that message will also increase the window size to 8,000. So the window size will increase exponentially. It's going to say, okay, now that you've sent 4,000 bytes worth of data successfully, you can now send 8,000 bytes worth of data. And so that's how the TCP window size increases. And now let's look at how the TCP window size would reduce size. So in this case, same example. Okay, the first packet arrived at the server successfully. Server responds back saying, okay, I've acknowledged receipt of that packet, and I've acknowledged receipt of all those 400 bytes worth of data. The next packet you should send should have a secret number of 722. I'm going to increase the window size to 4,000. Now, the client's going to send 3 packets, like in the previous example, to the server. But now one of those packets drops. Okay, one of those packets drops, okay? The server realizes, okay, I've received some data, but I haven't received all the data that the client was trying to send to me. I'm going to send an acknowledgement saying that I've acknowledged some of this. I've received some of the data that you've sent me. I'm also going to reduce the window size to 2,000 to essentially say to you, look, buddy, we've chanced our luck. It hasn't paid off. I've increased the window size. Packets have been lost now during transit. I want you to now let's lower it down, okay? I want you to send me only a smaller amount of data. Once I have successfully received, let's say, 2,000 bytes worth of data, then let's start to increase the TCP window size, okay? So that's the way that it reduces window size. The window size is reduced when data is lost during transit, data becomes corrupted, and then we essentially cut the window size in half. Okay, to say, okay, let's take it down a notch. You can now send me 2,000 bytes worth of data. Once I've now received those, I will now tell you, once I've received those successfully, I will say to you, now you can start sending me more data by increasing the window size, etc. Now let's see how TCP actually helps with the resending of lost segments. So obviously in the previous example, we saw how the 3 packets that the client was sending to the server, out of the 3, 1 packet was dropped, okay? So how does the server tell the client that that middle packet you sent to me dropped? I didn't receive that. The way that it does that is by sending duplicate acknowledgement messages. Okay, duplicate ACK messages listing the sequence number of the packet which was dropped. And so in this case, the first ACK message is going to send to the client, and it's going to say, okay, I received that first packet that you sent, but that's it. I haven't received any other packet that you've sent after that. Okay, now the client's going to think, that's strange, because obviously I sent 3 packets worth of data. I was expecting the server to respond back with an ACK message with a ACK number of 4722 to confirm receipt of all 4 bytes. So sorry, all 4,000 bytes of data that I just sent. But now he's responding back with a acknowledgement number saying that he's only received the first packet that I sent, the first TCP packet I think, which was 1,500 bytes. Okay. Now obviously the client is still going to keep sending traffic to the server. Then the server does something clever. The server does what we call a selective acknowledgement, okay? So the server is going to say, okay, I've received that first packet you sent. I've also received the third packet you sent. Can you guess which packet is missing? And again, it's going to, in the ACK message, it's going to list the sequence number of the second packet. Okay, because you have to remember that with the acknowledgement number not only tells the client that it's received the first packet, but also tells the client the sequence number of the next packet that it should send. And so through this process of duplicate ACKs and the selective ACK message, by saying to the client that I've received that first packet you sent, by using a acknowledgement number of 2222, I've received the third packet you've sent by using a acknowledgement number of 4722, but I haven't received the second packet you have sent because I'm listing the sequence number of the second packet as the acknowledgement number many times. I'm telling you like so many times that I haven't received this packet. Eventually, after a few duplicate acknowledgement packets that the client receives, the client is going to then retransmit that second packet. Okay, and then when the server responds back now with an ACK message, it's just going to list the ACK number as being 4722, meaning I've received all the data you've now sent to me. You can now start sending some new packets. Now, what happens when, in this example, imagine that the client sends some sort of data, okay, and then the server actually does receive it, but then the acknowledgement message is sending back to the client. What if that gets dropped or lost during transit? What happens then? Well, if the client doesn't receive a acknowledgement packet for the data that it has just sent within a certain amount of time, it's going to retransmit that data. So in this case, it sends some data to the server. The server receives it, sends back an ACK message, but it doesn't actually get there. After a certain amount of time, the client hasn't received any ACK message, so it's going to then now resend that data, and then this time, hopefully, once the data gets to the server is going to resend back an ACK message. The client will receive it because the ACK message will actually make it there, and then the client can now send the next chunk of data within that data stream. Now let's have a look at how the sequence numbering can help when packets arrive out of order on the server side or on the receiving end. So in this case, the client is going to be sending multiple packets to the server. So again, the client sent the first packet, which was acknowledged. The window size is changed to 4,000. It's now going to send 3 more TCP packets, okay, with sequence number 722, 2222, and 73722. Okay, in this case, okay, the TCP packet with sequence number 722 arrives first. The packet with sequence number 3722 arrives second, and then the packet with sequence number of 2222 arrives third. Using the sequence numbers, when it actually takes the data or takes these packets and then feeds them up to the application, it's going to send the first packet, so the packet labeled 1 first, is then going to send the third packet. Now, how does it know that that packet, even though it arrived last, should be sent to the application next? The reason being is because it has a lower sequence number than packet number 2. It's like, okay, so this is the first packet that I sent to the application because out of the 3 packets I received, it's got the lower sequence number. This is a second packet because it's got the next lower sequence number. This packet that I received second, even though I received this packet before I received packet 3, this packet should be sent to the application last because it's got the lowest sequence number and essentially represents a chunk of data further down the actual overall data stream of data that the sender application wants to transmit. So it understands that the lower sequence number, the further down the data stream this packet represents. And then how does sequence numbering help with duplicate packets? Okay, so in this case it's pretty simple. Packets 1, 2, 3, and 4, for some reason the client has transmitted packet 3 and 4 the same packet. So in this case it draws packet 4 because it's like packet 4 I received has got a sequence number of 2222. I've already received a TCP packet with that sequence number, so this must be a duplicate packet. I'm now going to drop that packet. And that's it. That's all there is to TCP. So as you can see, TCP isn't actually a difficult protocol to learn. Just to go over a few things, sequence numbers are very, very important. Essentially, they allow TCP to perform all the features that it needs to perform to be TCP. We looked at how with TCP, the 2 devices, client and server, are going to establish a TCP connection before any data is actually sent. During that connection, they will send and receive data, and we looked at how the actual sequence number identifies how far along we are in the data stream. And so essentially it represents that this chunk of data represents, let's say, the first 100 bytes in the data stream, the next chunk, the next 300 bytes, etc. And how the sequence number just dictates the actual how much data we've sent so far. And we've also looked at some of the TCP features. So next video, we are going to have a look at UDP, the User Datagram Protocol. Again, if you found this content useful and you want to see more content like this, please subscribe to my channel. If you found this video useful, please share so that we can get free, high quality IT training to the masses. Thank you very much.